follow along. On the next slide, you're going to see something like this. By the way, does anybody know, maybe you do, maybe you don't, but like, I know, like butane, B-U-T, do you know how many but means? Like 1, 2, 3, 4, 5, 6? It's 4. See, I guess you wouldn't know. Pent, how many does that mean?
5.
Perfect. Pent means 5. But actually means 4. How about hex?
6.
6. How about hept?
7.
7. So kind of going backwards. Prop, like this, prop means 3. So right away, and I know I taught this so many years, but I'm like, oh yeah, it's propanoic acid. I bet it's going to have 3 carbons. And actually that is correct. So anyway, and we'll talk more about those kind of the prop, but, pent and all that. We'll touch on it in this class. But this is different than before because it is a hydrocarbon, I say, with oxygen. So I'll put X, Y, Z. So we're going to try to find the empirical formula. It's going to combust with excess oxygen to, just like the video saw, H2O gas and CO2 gas. Actually, I usually do that the other way around. CO2, H2O. You know, and it's an unbalanced equation, granted. So that all works. And what we said before was that we count on all of this carbon from the thing that we're burning ending up as carbon in carbon dioxide. And then all of this hydrogen in the thing that we're burning ending up as hydrogen in water. So this is a classic. They give us the mass of the thing they're burning. Here's my little pile of solid CHO material, and it's 0.236 grams. And then they go ahead and they give us the mass of the CO2, 0.421 grams. And the mass of the H2O is 0.172. And then it's going to be kind of like we did before, where I'm going to go ahead over here and just make my little table. We're going to say element. We have carbon, hydrogen, and now we also have oxygen. We're going to come up with moles, and actually I'm going to add to this table. But that's kind of what we got going on. So we can go from the grams of carbon dioxide to the moles of CO2 using the molar mass, right? And then we can go from the moles of CO2 to the moles of carbon using the relationship. There's 1 mole of carbon for every 1 mole of CO2. We can do a similar thing, by the way. That mole's going to go right there. We can do a similar thing with regard to getting the moles of hydrogen out of this mass of water. So we can use the molar mass of H2O to get to moles of H2O. And then we can use the fact that there are 2 moles of hydrogen in every 1 mole of H2O to get to moles of hydrogen. And that number is going to go right there. The thing is, we got to do a little bit of kind of, and you're going to see this done in a little different order here. I think I did this right. So actually, we're going to take the moles of carbon in what we burned, and we're going to get to the do it this way. Grams of carbon in what we burned. We're going to use the molar mass simply from the periodic table, that 12.01 associated with carbon. We're going to use carbon's molar mass to get the grams of carbon. We have to do a similar thing here. How much hydrogen was there in what we burned? We know how many moles there were, so we need to use the molar mass of hydrogen to get to the grams of hydrogen in what we burned. The reason we got to do this is we're going to take these 2 grams and we're going to subtract it from the mass of CHO. Okay, so we have the mass of what we burned. We subtract how much the carbon was. We subtract how much the hydrogen was, and that will give us the mass of oxygen in what we burned. So that's the story. That's my story. That is the story. I'm sticking to it. Of course, then we can go, I guess I should add this. And we can go from the mass of oxygen to the moles of oxygen using the molar mass of oxygen. And that moles of oxygen finally will go here. And then finally we'll have a full set of 3 moles, and we can divide by the smallest and kind of do it like we did it before. So there's a few steps, but that's kind of generally, I don't know if that helped, but that's what it is. So focus on the carbon dioxide. We're going to ultimately go from the mass of carbon dioxide at 0.421 grams all the way to the moles of carbon in the sample. So if we start 0.421 grams of CO2, of course we're going to use the molar mass of CO2. You guys would have to show me this calculation, but we're into a few problems anymore, and I'm just going to tell you that CO2 has a molar mass of 44.01 grams per mole. So we're going to do 1 mole of CO2 over 44.01 grams of CO2. Now sometimes I say you don't have to put the CO2, but this time you have to put the CO2 because we're going to, here, one of our next steps is to get to moles of carbon. So how many moles of carbon are there in 1 mole of CO2? 1. Yes. So it's going to look like this. 1 mole of carbon over 1 mole of CO2. And ta-da! 3 sig figs. So you got a few placeholders there. So 0.00957. So that goes here for my moles of carbon. You don't have to do a table like this, but I like it. Okay, so that was that. Now we're going for the moles of hydrogen from the mass of water. So the mass of water was 0.172 grams. What's the molar mass of water? There we go. 18.02, very good, grams per mole. So we'll use the molar mass this way. 1 mole of H2O over 18.02 grams of H2O. So what does that, the next term look like to get to moles of hydrogen from moles of H2O?
2 moles of hydrogen for 1 mole of H2O.
I agree, 2 moles of hydrogen for 1 mole of H2O, perfect. 3 sig figs? Okay, so that means the moles of hydrogen in the mass I took to combust is 0.0191 moles of hydrogen. Okay, and see, I figure if I label the column, then I don't have to put the word moles there. All right. Well, what I said next is we have to kind of tease the oxygen out of it. So to tease the oxygen out of it, we have to take these moles and convert them to grams and then subtract that mass from the thing we burned. So to get to the mass of carbon, we're going to piggyback on this moles of carbon. So the first term is going to be 0.00957 moles of carbon over 1. And straight off the periodic table, the molar mass of oxygen is 12.01. So then we can put 12.01 grams of carbon over 1 mole of carbon. And 3 sig figs. So you're looking at 0.115 grams from carbon. We're going to do a similar thing with hydrogen. We came up with the moles of hydrogen, 0.191. So 0.0191. 0.0191 moles of hydrogen. What's the molar mass of hydrogen?
1.008.
Yep, I use 1.008. Yep, 1.008 grams per 1 mole. You guys have been doing some chemistry problems, I can tell. Yay! Ooh, bless you. So 3 sig figs, you're looking at a mass. Bless you. In the sample that you burned, you're looking at 0.0192 grams. Of the hydrogen. You know, and this is where, like, if you were to somehow come up with a mass down here of your carbon and hydrogen that's greater than the mass of the thing you burned, something went wrong, terribly wrong. But we should be okay. So on the next slide, what you're going to see is we're going to take this mass, and from it, we're going to subtract these 2 masses. So the mass of the thing we burned, which has carbon, hydrogen, and oxygen, is 0.236 grams. The mass of the carbon we came up with was 0.115 grams, so we're going to subtract that. And then we're also going to subtract the mass of the hydrogen at 0.0192 grams. Grams of hydrogen. Now, we don't do a lot of it, subtracting and addition, adding like this. So what we have to go with decimals. So you figure I have 4 decimals for the mass of the hydrogen, but 3 and 3 for the sample. So that's why, regardless of what the calculator displays, we're only allowed 3. See, it's just a problem that it feels like it keeps going and going, but I guess it's not been that long. Because now what do we have to do with that grams of oxygen? We have to convert it to moles, exactly. What's the molar mass of oxygen? It is 16. Sweet 16. So our first term is going to be that 0.102 grams of oxygen times 1 mole of oxygen over 16.00 grams of oxygen. Now this is where, like, when you take your test next Thursday, you'll have lots of time. You guys, most people really don't need 2 hours. So I say that because if you have a term like this one, I want to see 16.00. It's a different number than 16. Okay, good. So 3 sig figs. So I could put, and I will put, 0.00636 moles of oxygen. Well, I have slides to kind of finish out, but I'm just so excited now. Let's go ahead and do it like I like to do it with this table. What will I divide by?
Oxygen.
Yep, the oxygen. Yep. So divide by 0.00636. And so if I go 0.005, sorry, 0.00957, 5.00636. Oh, I got a halvesy. Drat. 1.50. So I'm going to have another column times 2, aren't I? So what if I take 0.0191 divided by 0.00636? Oh, well, that's nice. 3.00, and of course this is 1.00. So yep, I need one more column. It's going to be times 2. So 1.5 times 2 is 3.00. 3 times 2 is 6.00. 1 times 2 is 2.00. So these then are my subscripts. So you're looking at C3H6O2. Again, the whole that better be a 3 because it's referring to the number of carbons. Any questions about that? So here's how my slides go. So you see we're taking it relative, like you said, to the oxygen. I focus first on the carbon relative to the oxygen. You're looking at 1.5. Scaling it up times 2, both the numerator and denominator, you're looking at 3 to 2. Okay. And so with regard to this just confuses me, I think, but it makes sense. With regard the hydrogen relative to the oxygen, look at 3 to 1, but we're going to have to go with 2 up there, so it's really 6 to 2. Okay, so you get the same empirical formula. You should. Okay. What's that? So this is just your reminder when we, when I did my first division and I came up with a 0.5, I knew I had to clean it up by multiplying it by 2. The other things, like the slide warned you about, is your 0.3s, 0.333 or 0.6666. You multiply by 3, things fall in place. Your others are the quartersies, which would be 0.25 or 0.75. So this type of approach, it can lend itself to other type of analyses where something, for instance, the carbon is only in the carbon dioxide, the hydrogen is only in the water. That makes us able to unravel it, just like we did. But it doesn't have to be a combustion analysis like this. Hint, hint, wink, wink. I think you have homework problems that are going to kind of make use of that fact. All right. So can I erase this beautiful artwork up here? Okay, going. Here is another one. I like the title of it. What is it? A non-stoichiometry problem. Because we're used to stoichiometry problems using a ratio from the stoichiometric coefficients from the balanced equation. And we're not going to go that route, although I think we could. But we're not going to. I don't know. I have to look at the problem again to see if we could. Hydrocarbon. So a hydrocarbon is just this, CHY. It's going to react with excess oxygen, combust. And it doesn't say it, but we know it, CO2 plus H2O. It says that the hydrocarbon was determined to be 81.7% carbon. So, yeah. And it says that, maybe I'm going to put that above it. Then I'll put my mass down here. The mass of the sample that was burned was, here's my blob of sample that was burned, is 2.89 grams of the hydrocarbon was burned. And what we're trying to get at is the mass of CO2. So question mark grams. You see where it seems like what we've done before is to go from mass of CXHY to moles and then use the stoichiometric ratio to get to moles of CO2, use the mole mass of CO2, okay, to get to grams of CO2. The problem here is we don't know X and Y, so you can't get a mole mass for that thing. Okay, so this actually then is the unbalanced equation. But we're going to take advantage of what we've been taking advantage of before, that all of this carbon is going to end up as, the carbon in your sample that you're burning is going to end up as carbon in your carbon dioxide. And then I have this diagram to kind of talk us through it. We can go from grams of compound to grams of carbon using the weight percent. Oh, my shift key. Does that make sense? Grams of compound to grams of carbon using this weight percent carbon. Make sense? And then we can go from the grams of carbon to the moles of carbon using its molar mass. And then we can go from, let's see. Then we know that all of those moles ended up as moles over here. This is going to be the same. So then we can use the moles of carbon in the moles. We can use the moles of carbon we have to get to the moles of CO2 using the fact that we have 1 mole of carbon for every 1 mole of CO2. And then we can use the molar mass of CO2 to get from moles of CO2 to grams of CO2. So we don't have to know the X and the Y, but we did know you need to know the weight percent of carbon. So let's do it. And I think there's like only one slide left maybe. So it's going to be one big run-on problem. So you're going to have to carefully label all the species that are involved. So our starting, we're going to go with a 0.289 grams of compound. I have to say compound because I don't know what the X and the Y are. 2.89 grams of compound. And then I'm going to use the weight percent. That by definition, that means I have 81.7 grams of carbon for every 100 grams of compound. So how would I use weight percent? What would that term look like?
87.1 grams of carbon over 100 grams.
Exactly. 81.7 grams of carbon over 100 grams of compound. That's by definition what weight percent is. So how can I get to moles of carbon then? Molar mass of carbon. Yeah, what you guys told me is 12.01. So we're going to have to use the 1 mole of carbon over 12.01 grams of carbon. Perfect. And so then we're like over here. So how do I go from moles of carbon to moles of carbon dioxide?
Carbon. 1 mole of CO2 over 1 mole.
Yep, 1 mole CO2 over 1 mole of carbon. Perfect. Does anybody remember the molar mass of carbon dioxide? You will after you do all these problems this weekend. It is 44.01, yep. So if we go with 44.01 grams of CO2 over 1 mole of CO2, voila! And on this one, you know, I haven't canceled terms, but grams of compound cancel. I just love the canceling part. Grams of carbon cancel. Moles of carbon cancel. Moles of carbon dioxide cancel. We're left with exactly what we were after. The grams of CO2. 3 sig figs. So you're looking at 8.65 grams of CO2. So just know, like, I'm trying to think if, and I don't want to say that I've never had one of these like this on the test, but I can't remember ever having one like this on the test. Test is made out yet. Okay. Any questions? Yay, we're out early, and it's Friday and it's rainy, but.
Did you see it was like snowing around there?
I saw
It was
that.
snowing?
Yeah.
Big old flakes.
What?
Last night I got my telescope out though, and I got a picture that's faint of the Helix. It's called the Helix Nebula, and I got a pretty good picture of it's low hanging fruit, but the Ring Nebula in Lyra. So,
Oh, sweet.
so that was fun. But yeah, snow.